So let's start. Really glad that you are listening to us. We want to tell you about our journey from single Kaggle case to AutoML solution. This is the overview of our journey. So everything started from a Kaggle challenge that was aimed to impress our new client. And of course, we started with conservative approach, like normal job that is done by us as data scientists day to day. Then we tried many different tools. Like we need to do something impressive, and that was the third step. And finally, we realized that creating our own AutoML solution may be what we're looking for to be impressing. But let's move on step by step, and let's start from the first one, from Kaggle case. Um, you all know what's Kaggle, right? And we had their canonical case for client classification. That's a data set from a home credit organization. They provide loan products to their customers based on the probability, based on their reliability, based on the probability of default of customers. This data set has many tables with their relations, actually 7 data tables. And the task for this competition was to predict if the particular client gonna default based on historical data. So this is a task for supervised learning. The evaluation was done based on ROC AUC metric. The leaderboard was in place, and let's see some more features of this competition. So first of all, it's pretty crowded. It has more than 7,000 teams who participated in this competition. It has, as I mentioned, 7 related data tables, and you can see the data structure on the image. Main table is application, train and test set, and then foreign keys relating this data set to others like uh, credit bureau, post cash, installment payments, and other tables. In total, for 7 tables, there were around 300 features, even more than 300 features. Main table included 120. And the main table also included, train and test data sets. They had 350,000 records in them. And the data set was slightly imbalanced. It means that defaults happened only in 10% of cases. So these are the main challenges. And now let's take a look uh, on what we done as a basic step, as a step number one. Uh, so actually, how we approach this competition, right? Um, First of all, we created a baseline model with one data set. Pretty straightforward task. We did exploratory data analysis, understood better what's in the data set, what has to be done with it, then some basic data preparation, cleansing of data, handling categorical features, continuous features, so standard stuff. Running baseline model and optimizing it, which gave us 75% AUC, which is quite good only for one table, but for sure it's not enough to impress. Then, of course, we had to join other data sets, and we combined all 7 data sets manually and started feature engineering, also manually, just taking some aggregations, averages, and so on. We also played with different models. LGBM appeared to be the most promising. We did cross validation and model optimization, and that's allowed us to show the result of 78.19%, which was not bad, top 30% on Kaggle. And from this stage, we needed to move on. And we also, the stage was enough for us to understand which most common issues can we face in such tasks or similar tasks. So first of all, as we've manually merged data sets and tried feature engineering, we realized that we may be missing and were missing the important features. That's on the one hand. On the other hand, we were creating a lot of noise, means useless features that are not helping the models. They're just even they even can reduce the scores, right? The next problem was that descriptions of the features were purely in our POC code, so they were not clear to domain experts and they were not interpretable. Uh, the next one, the next issue was about um, feature engineering itself. Like if this we are talking about simple features, like multiplying one column by another one, then it's pretty straightforward. It can be handled just by pandas, and that's it. But if we talking about features with more complex aggregations from many tables with some splits of data and so on, then usually it requires vast computation resources. And as more feature you use, as more tables you use, you need more of these resources. The next issue was the fact that the local trials are limited by the size of data set and the power of this local machine on which you run your local trails. And the number 6 that you can see, a new prediction target. So actually in this case it was not critical that we have only one prediction target, the probability of default. But in general, in real business cases, there are often several targets, and it's nice to be able to do feature engineering, to generate data, to prepare data and reuse it for many cases, not just have it for only one. So these were the issues that we have identified. And now it's time for our third step in our journey, trying many different tools. And now, Dmitry, the floor is yours.
Thank you, Vlad. So we started thinking how we can improve our score, and our first idea was to try some AutoML tools which out of the box provide us the best results doing all feature engineering steps together with model selection steps. So overall, AutoML solutions has like two buckets: open source bucket and cloud-based bucket. So if you will be looking at the cloud-based buckets, you will see the top players on the market. It's AWS with Amazon SageMaker Autopilot. It's Azure Machine Learning Studio with AutoML. It's Google with the Vertex AI platform, which can also work not only with tabular data, but also with computer vision tasks and machine translation, natural language processing. And IBM Watson and DataRobot, where DataRobot was one of the first companies at all who started doing AutoML tooling for machine learning problems. And open source tools like AutoEscalar and TPAT, H2O, AutoGluon, MLJar, MLBox. So AutoGluon is an open source tool which can work with time series data and which is actually used and made by AWS inside SageMaker, and it's part of tooling that is open source. So we tried all of these tools, and we saw that still we may be better in modeling stage, but still we have a big gap with data preparation and merging data sets and feature engineering. So we moved forward and we started looking for the tools which can provide us better feature engineering support. So we started with feature tools, which automates feature generation process. It's also open source and it's like state of the art in automating feature generation process. It has some pros, so it can work with relational data tables, which was our issue in the beginning. It has many functions for new features creation and generation. It can be partially parallelized using Dask or Calus data frames. Still, it is in beta and it has some nuances, but still, feature tools can provide out-of-the-box partial support for generation of the features with Dask. But still, it has some cons. It's quite slow and unoptimized. You cannot generate really fast hundreds and thousands of features. And most of the time, feature tools just generate a huge number of all feature combinations, and that's all. So you have to decide what to do with those, what are the best features, and it's like helping only on the half with our feature generation. So we moved forward and we made a GetML tool which uses this interesting feature learners approach. It is not open source, but still it has interesting pros like C++ self-written database agent, which can speed up computations, and really local trails would be very fast. It can generate features using straightforward way, same as feature tools, and can be used with tree-based approaches, which is also a very interesting one when you're required to train a tree-based model, and it will generate features for you. It can work with relational datasets. It has some UI with the details of your features and datasets. And all feature generation approaches are transpiled into SQL. And this is pros, both, and cons, because you can see that SQL, an example of the SQL query for one feature generated with this tool, and the feature name is feature 117, and this is the sum of some really strange numbers with Y and DS value from the basic dataset, basic table, and it is the biggest cons of this library. It is almost not interpretable. So you cannot look at the feature name and say what's happening. When you have like hundreds of features, they will look like this, and it's really hard to understand for business what these features mean. It takes still much time for feature generation. The more relations, the more data, the more time needed. And it must be fine-tuned, because in the core of the system, some tree-based models are trained, are fine-tuned with some Hyperopt algorithms, and you have to wait till you have some like great scores. So it's interesting approach, but we move forward and we decided to try neural networks, but not for the model selection stage. We started to thinking of approach how we can generate the features using neural networks. So we tried to train multiple neural networks with different feature combinations that were predicting another feature from this data set. So you can see on the right side features in blue that are base features from our data set, and T is a target, which is another feature from this data set. So we trained this neural network, and we are removing the target, the output layer, right? And we take the previous layers before the target, and we got their weights. And we treat these weights as a new feature. So we can try any model we want to. We can build models containing not only this feature, but basic features too. And results were interesting. So we had some features that became important, but still it's only the weights and the numbers, and the features were not really interpretable. So we again tried different tools, but got not impressive scores. Yeah, we found something interesting, but still it is not something impressive because the tools already are built and everyone can use those. So we started thinking how we can turn those cons and pros into our own solution and consider it as better and make it better than all tools that we tried, and try to bake all experience that we have using these tools into our custom AutoML solution. So we started thinking of the challenges we faced previously, which Vlad was already describing earlier today. And we thought of features which we need to do to implement that can improve and solve the challenges on the left side of the table. So we thought that, yeah, we need to produce a lot of features based on different data tables and their relations. So that's our source of increasing the score. We knew this. Also, we knew that we need to remove unimportant features, because there should be some way to understand from thousands of features which one would be the best, because in production you will not use like millions of features, right? And we should know what are those features. So we need to explain those. We need to have feature information of the created features. And This feature engineering, this whole solution should be run in iterations in parallel, and it should be run on clouds, in any cloud, and on premise actually. And the targets which can be defined in the beginning of our tool should be easily be changed, that the business can just select other target or select multiple targets and get the best data sets for predicting those targets. So with all of these, we created our custom AutoML solution, which solves those features and puts on the next level AutoML tooling for relation data tables. So if you take a look at the basic pipeline on the top of the screen, we already talked about it with Vlad, that we manually merged our data sets. We did some manual feature engineering. We trained some models, made an experiments, and optimized those. And this usually takes 10 to 15 days for a original data scientist, right? But our pipeline has 4 automated steps and only 1 manual steps, and it runs 3 to 5 times faster than the whole manual pipeline. So we are starting with 1 manual required step for data in relations specification. So we need to define relations between the data sets. We need to upload those data sets, define the target value. Then we run our fully automated pipeline that has advanced feature engineering step, which is the most important here in our pipeline. It generates millions of new features in parallel on any cloud, on premise, or again, any cloud. It does feature selection, which selects the best features, and it can be supervised and statistical. Also, we have model selection stage, which does cross-validation. And on this stage, we got IUC metric 0.784, which was even higher than the biggest and highest metric on the last step of the manual pipeline. But we didn't stop here. We got some model optimization techniques. We run hyperparameter optimization, and we got our AUC metric up to 0.797, which got us to top 3% of Kaggle, which is really wow. It is really great result with only automatic pipeline without data scientists involvement. But again, we didn't stop here. We did an optional manual feature engineering step with data scientist involvement and model optimizations. And we got AUC metric even higher, above 0.8, which got us to top 0.6% on Kaggle, which is really great example here. So I would like to describe advanced feature engineering step in details. So it aims at relational data sets. It used hundreds of predefined feature generation schemas, and we can manage feature complexity in the beginning of the pipeline with just a setting. It uses feature selection techniques very closely to feature generation techniques. So we'll get the best features on each iteration that we can. And it can parallelize horizontally and vertically in any cloud and on-premise. And you can see on this diagram that we just loading feature generation schemas on the cluster. It runs in parallel any number of nodes where we have this feature generation and feature selection steps inside, and then we have feature selection step in final, and we get the cleanest and the best features for our problem, right? So how we can scale it? We can scale it in 3 ways. Actually, we have local mode, which we can run just Dask cluster on the local machine, and you can do this with Python multi-threading. So you will utilize all the CPUs and all memory on your machine to create the new features. We have remote virtual machine mode, when the Dask cluster may be deployed in cloud with remote Dask workers. And also you can have local Dask cluster master, and it can connect to Dask workers in the cloud. And we also have remote Kubernetes mode for the big data, for big and long computations, where we have Kubernetes cluster in the cloud. Inside we have desk master, Dask workers, any number of workers, so you can parallelize it and get the best data set for your problem really fast. So to come back to our Kaggle competition, you can see these sharp plots with the features from the Kaggle competition, and you can see really complex but still interpretable feature names. These are the tables from these 7 tables Vlad already described, and this gives us the best results that we could achieve with auto pipeline. So I would like to pass back to Vlad to summarize what we achieved in this Kaggle competition and to see the summary of those.
Yes, thank you so much, Dima. Um, Now it's time for summary. Our biggest achievement, our Everest, is the fact that we've uh, could go above 80% AUC, which is pretty high, and that's the highest. You can see that the highest score in competition for 7,000 teams is a bit higher. It's 80.57%. Our DataML solution in automatic mode got to top 3%, which means that this AutoML solution out of the box could gain a silver medal on Kaggle competition. You can see what does it mean. So for such competition of such scale, with more than 1,000 teams, it means that we are in top 5% by our score. And it's like out of the box with just manual efforts to merge data sets, and then it goes on by itself. And of course, as I mentioned, with having this results as the basics, it's pretty. It's not easy, but it's easier to advance from this starting point. And if we remember our challenges and features that we plan for uh, the AutoML solution, that's on the next slide, we can tell that first of all, we could generate, um, for this particular case, we generated 1,300,000 features. And from this huge amount, we've selected only 4,200 features that were useful for the models. We also introduced feature to have multiple prediction targets. It means that part of generated features may be useful to predict default, like in our case, and other features can be useful for other things. And regarding a couple of more features of our DataArt's AutoML solution, we I can say that feature generation schemas is a great stuff as they stored separately, and they are used to run the computations, and also they are used as the explainable uh, blueprints of the features. Uh, and advanced feature engineering can be run on single machine or on cluster on multiple machines. And we've added a simple configuration in a file that is just one property in configuration file that allows to run the same pipeline on local machine or in cluster, in cloud, or on premise. So just to wrap up the highlights of DataArt's AutoML solution, we strongly believe that this AutoML solution is an advanced starting point for any data science team. As in our example, you saw that after the automated processing, the scores were even better than after the weeks of the manual work. And it actually saves time. In our case, it was up to 3 times. Maybe it of course depends on the case complexity, on the number of tables, and so on, but it's a real time saver. Our solution is focused on multi-relational data tables. It's especially useful on such cases, and in my experience, those are the majority of cases because data is not usually stored in a single table. It's stored in complex data warehouses, databases with complex relations. Our solution is empowered by web application and SDK. It's scalable. you saw Dmitry was showing the architecture of this solution for different modes, and these modes actually support cloud. It's cloud agnostic. It can run on GCP, AWS, Azure, and also can run on-prem. And this solution is not specific for a domain. It's domain agnostic. It means it can be used in finance, insurance, travel, hospitality, media, and so on in any industry with tabular data and with massive relational database structures. So yeah, that's it. That's the what we wanted to tell you today.